All right, in this video, we're going to look at the intermediate value theorem. And the intermediate value theorem informally says that a continuous function cannot skip values. So let's just start with that intuitive graphical understanding. So let's just say I have a function on the left here. It's continuous. Let's just call it f of x. And let's say that this is a. So I'm going to kind of extend that downward. That would mean that this y value there we'll call f of a. And let's say over here we've got an x value b. That means that that point has a y coordinate f of b. So now I'm just going to trace this graph from a to b. We can see it goes up. It assumes these y values. Looks like it goes down and goes up. Continuous function. I never needed to lift my pen. And go to the y-axis now, we can see every single y value between f of a and f of b got, quote, hit. So let me just kind of write that informally. Every y value got hit. Okay, meaning there's always a point on the graph that has an x value that yields an output for every y value in between f of a and f of b. When your function's not continuous, that's not guaranteed. As we can see in this example, let's say this is a, so that this value here is f of a. And let's just say here that's b, so that means that this y value here is f of b. Okay, so we start tracing the graph. We start here. We start tracing it from a to b. There's a jump, so I have to lift my pen, and we end here. And so we can see that there are some y values that didn't get hit, right? These y values did not get hit. There are no x values that produce outputs for any y value in that window. So I'm just going to note these y values didn't get hit. Okay. So one last point to make is that even though it's not guaranteed that for a discontinuous function all the y values get hit, it still could happen. So for instance, in this graph, let's call that a, so that this point has coordinates f of a, and let's call this point b, so that this has a y coordinate of f of b. We trace the graph from a to b. We trace it. We jump. Okay. As it turns out, if you look carefully, I'm going to start tracing on the y-axis. All the y values that got hit are all these, right? And actually, all of these got hit too. So all the y values got hit in between f of a and f of b. All the y values got hit. Okay, so even though it's a discontinuous function, it's still possible for all the y values to get hit, but this isn't guaranteed. Okay, this isn't guaranteed. For discontinuous functions. It is guaranteed for continuous functions, as we saw up here on the left. So that's what we explore. Calculus is mainly a discussion on continuous functions. So here's the formal definition, and I'll just talk briefly about some of its applications. It says if f of x is a continuous function on the closed interval a to b, and d is a number between f of a and f of b, then the intermediate value theorem guarantees that there is at least one number c between a and b such that f of c equals d. So just a quick picture to illustrate here. Okay, say that's a and that's b. If this is my function, That would mean that this is f of a, and this up here is f of b. And what they're saying is d, right? If d is a number between f of a and f of b, no matter where you put it, let's just say d is here, right? Because f is a continuous function, there will always be an input that will yield that output, right? So f of c clearly equals d in our picture here, and that's guaranteed that there's at least one of those, at least one, that will produce that output. So some applications of the intermediate value theorem: one is finding solutions to equations, or proving that such solutions exist. So for instance, this says prove that x cubed equals 12 has at least one solution on the interval 1 to 5. So typically the way this is done is, notice we have an equation here, not a function, and the intermediate value theorem is defined in terms of a function. But that's okay. What we tend to do in this case is just change this equation to be x cubed minus 12 equals 0, and then just define f of x to be x cubed minus 12, and we want to show f of x equals 0, or I should really say f of c equals 0 for some c in the interval 1 to 5. All right, so let's just evaluate. We're looking at the interval 1 to 5 here. Let's evaluate f of 1. That's 1 cubed minus 12, so that's negative 11. And f of 5, on the other hand, is 5 cubed minus 12, which is 125, minus 12, which is 113. Okay, so clearly we can see 0 is in between negative 11 and 113. I guess the other thing I should point out is that f of x is clearly a continuous function, right? It's a polynomial, which are always continuous. So what this implies is, since f of x is continuous by the intermediate value theorem, there must be at least one c such that f of c equals 0, which implies that f of x equals x cubed minus 12 has at least 1, 0 on the interval 1 to 5. Okay, so yeah, it's an existence proof here, and it's probably, given all the technology we have, you probably file that under something that's obvious, but it's not always obvious when you're given a function that there exists zeros. And in fact, the intermediate value theorem is used a lot in computer science to find zeros for functions that are not easy to handle using algebra. So just one last example I'm looking for is not here. There it is. This is the example I wanted to go over. So it says if f of x is continuous on a to b, and if f of a and f of b are non-zero and have opposite signs, then f of x has a 0 in a to b. This is similar to what we just did above. But let me just note that f of x equals 2x minus cosine of x is not that easy to analyze algebraically. Okay, you've got a mix of a trigonometric function and a polynomial function. But because cosine and 2x are both continuous, when you add and subtract continuous functions, you get another continuous function. So we know this is continuous on its domain. So in particular, it's continuous on the interval 0 to 2. Okay, so let's just prove here that it has a 0. So we evaluate the function at 0, which would be 2 times 0 minus cosine of 0, which is 0 minus 1, which is negative 1. Okay, so that's less than 0. And then f of 2 equals 2 times 2 minus cosine of 2, which is 4 minus cosine of 2. So we could cheat here if we had to and go plug in cosine of 2, but the biggest cosine can ever be is 1, which means that the smallest 4 minus cosine of 2 could be is 3. So in any case, we know that this is greater than 3, which is clearly greater than 0. And so now we see that f of 0 and f of 2 have opposite signs. And that proves that, so therefore, by the intermediate value theorem, f of x has a 0 on the interval 0 to 2. Okay. I mean, technically, we would just say there exists a c such that f of c equals 0 at least once on that interval. And for those who are, looking for, again, an application of this, there's something called in computer science or computer programming called the bisection method. Okay, the bisection method is an algorithm. It's like a loop algorithm that helps you find zeros once you appropriately program your computer. So to approximate or find zeros to whatever level of accuracy you want. Okay, but in any case, that's the intermediate value theorem. It's intuitive. It's actually pretty hard to prove, as it turns out, but hopefully this video gave you an overview of the things you should think about as you go forward.